Hello, welcome back. In the last lecture we had discussed about stability analysis, of course, with respect to matrix stability analysis, and also worked out a couple of examples. So, let us learn today Fourier series stability analysis. So, as the word suggests, Fourier series stability analysis, the main idea in this is the initial error is expanded in terms of a Fourier series, and then look for a condition restricting the amplitude. Okay. So, let us discuss Fourier series stability analysis. So, as the title says, Fourier series stability analysis, also this has another name, von Neumann stability analysis. Okay. So, what is the idea? As I mentioned, assume that the initial error is expanded in terms of a Fourier series and obtain conditions restricting the amplification. So, this is the main idea. So, let us even instead of discussing more general case, we can consider couple of examples and then learn the process. Okay. So, consider explicit scheme, which is a Schmidt's method. Okay. If we consider this u I j plus 1 so Schmidt method. So, now we would like to introduce the error. So, if we introduce the error, error satisfies epsilon I j plus 1 is epsilon I j okay. So, this is the error. Now, as I suggested here, we have to assume the initial error in terms of Fourier series. Okay. So, in order to do that, let us see couple of things. So, this is our x naught is a, then x n is b, assume that L is b minus a and x naught plus m h, where m is 0, 1, 2, n. So, accordingly, this will be n h. Okay. Now, for convenient purpose, because we have to expand in Fourier series and there we are going to introduce the notation I, which is due to the complex notation, complex variable notation. So, not to confuse with the normal indices, we introduce this notation. So, for this is our usual practice, so far we have been following, but this may be introduced like this, where this is at any point which is p h q k. Okay. So, this is the notation now we are going to introduce. Further, initial values at t equals to 0, u of p h 0, u of p 0, so instead of I we have introduced a p, instead of j we introduced a q. Okay. Now, initial error, so this we expand it as follows: initial error a n I beta at any point. So, this is x, then e power alpha t. Okay. So, this is a Fourier series expansion. However, in this case I beta p h, but at any x I or t j. So, x p and t q. So, this will be e power alpha q k. So, this is our initial error. Okay. So, this when we have expanded, this should be restricted at t equals to 0. So, this is a general expansion. So, therefore, p h. Okay. So, which means the general notation is this is what for summation over q a q e power I beta p h e power alpha q k. Okay. So, this is a more general. So, whereas this is for t equals to 0 initial expansion. Okay. So, now with this notation, so we introduce further simplified notation zeta power q, where zeta is e power alpha k. So, what is the need of introducing this variable? See, the error at time t equal to 0 is plugged in into the system, and we are observing at subsequent time steps the amplification of the error. Hence, the variable which we are going to observe should be related to the time. So, this is the variable. Okay. So, now note that the scheme is linear. So, we just consider one term. Okay. We just consider one term as follows, with a constant just okay, and we call zeta amplification factor. Now, Lack's theorem, this says finite difference scheme is stable if mod UPQ is bounded. So, accordingly this implies, so this is bounded. So, when this is bounded only when the corresponding condition on amplification factor. Okay. So, let us substitute this in our, so substituting star form in E. So, what was our E? E was the equation satisfied by the error, difference equation satisfied by the error. So, if we do this, what we get as follows: A I will show you why this is. This is A this power Q plus lambda A H plus so please look at this. We have this is nothing but epsilon PQ and this is expanded as AQ and e power alpha QK, and this is nothing but, so P index is for H, Q is for K. So, now we have here Q plus 1. Okay. So, it is in some sense we need this. So, I have transferred I to P and this of course, we have to adjust. So, this is generic notation, but we need it for Q plus 1 here, Q here, Q here and Q here. So, accordingly you can see Q plus 1 to the left hand side and Q on the right hand side. And similarly, I minus 1 corresponds to P minus 1, I plus 1 corresponds to P plus 1 and I corresponds to P. Okay. So, because we have this index earlier and now this is a complex notation. So, I changed it. Okay. Now, some terms cancel. So, after cancelling these terms, so for example, this goes one term. Okay. So, then we get, so this entire get cancelled, one zeta left, and here of course, we have some extra terms left. There is a minus I beta H and here we get a plus. Okay. So, this can be simplified 1 plus lambda minus 2. So, I have taken this term inside. Okay. So, then this is 1 plus 2 lambda. So, this is just an adjustment. So, now for stability we need so this implies we get lambda is less than or equal to 1 over sin square beta h by 2 for stability, and since this is less than or equal to 1, this quantity we get this implies 0 less than lambda less than or equals to. So, this is the region of stability. Okay. So, this is the region of stability. So, now exercise. So, consider the loss on an implicit scheme approximating show that the above scheme means Larson scheme is unconditionally stable. Okay. So, that means for all lambda, so we get stability. Okay. So, the technique is also very interesting compared to matrix stability analysis, because the initial error has been expanded in terms of Fourier series and then plugged into the difference equation satisfied by the error, and then restricting the amplification we find out the region of stability. Okay. So, let us work on several other schemes, so that we get it better. So, for example, given the approximation okay, use Fourier series stability method and find the region of stability. Suppose this is given, then we would like to solve this. Solution. So, the equation is finite difference equation So, now accordingly the equation satisfied by the error we have to follow the index notation carefully. So, this is epsilon. Now, considering the expansion of the error, this will be, so I am dropping the constant p h, and this will be so this is the error equation. Then after some cancellations we get so we get this, and further simplifying. So, this will be 1 minus 2 lambda. Okay. So, then imposing restriction on the amplitude amplification. So, this will be lambda less than or equal to 1 by 1 minus. Now, we need a tighter value, that means tighter bound. So, correspondingly we may get 2 in the denominator. So, therefore, lambda is less than or equal to half. Okay. So, this is the corresponding stability region. Okay. So, let us see some more problems, because this is a general. So, general, if you introduce any general coefficients, still the process remain the same. So, hence I prefer to discuss lot of examples. Okay. So, discuss the stability of the finite difference method approximating So, here A and B are constants. Okay. So, again we do the same process. If we do the similar process, we get the equation satisfied by the error is so I pull out, because these two are having index p with respect to x. So, I have pulled out. However, here this has index q plus 1, this is q. Then when we transfer k by h square, that is a lambda here, then corresponding to p minus 1, this is the index, corresponding to q, this is the index. Plus we have taken k to the right hand side. So, therefore, here we have k b okay. So, this on simplification, because zeta power q get cancelled. So, here lambda a by 3 so, we get this. So, this can be simplified k b, and if we restrict the amplification, this will be so this so k is positive, b is a positive constant. So, this implies lambda is less than or equals to. So, if we need, then lambda is 3 by 2 a. So, this is the corresponding region of stability. Okay. So, this gives more or less some idea about both matrix stability and Fourier stability analysis. So, before we go to the next topic, let us spend some time on a few examples where also matrix stability is considered. Okay. So, accordingly my next example will be where we have matrix stability is considered. Okay. So, matrix stability Crank-Nicolson scheme we have discussed, but we discuss in a different way. So, consider the scheme Okay. So, now we have discussed the stability of this method via error equation, in the sense we have obtained the corresponding finite difference equation satisfied by the error, and then we obtained an estimate. But in this case let us go through formal matrix stability analysis. So, now this can be rewritten as so when I equals to 1, this becomes a boundary term which is known. So, we push it to the right. So, the first non-zero term is this, next one is this accordingly. So, these are the unknowns. This is equal to, you can see here, so dot 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 u1j, u2j, u n minus 1j plus b I. So, this contains boundary values and zeros. Okay. Then this can be expressed as so you may recall our earlier notations. I will explain. So, what is done? This is split up into two matrices. One is 2 times the identity matrix, because everywhere you have 1 1 1. Then the other one is lambda times this is supposed to be this terms. So, we have split it into two different matrices. So, accordingly 2 times identity matrix, the other one is T n minus 1. So, we get this. Then u j is a j, u j is a j, u 0, f 0, f 1, f j minus 1. How did we get this? So, this was our notation. So, that is what I suggested, to look for the other notation introduced earlier. So, this is a u j plus this is our f j. Okay. So, this can be first put it in this form, then we iteratively expand. Okay. So, by comparing these two, we get A is So, this is A because B inverse and C. I think there is a small, see when we split this. So, 2 into 1 plus lambda and here 2 into 1 minus lambda. So, when we split this, please correct it as this must be plus and this is minus. So, accordingly minus. Okay. Now, we have to compute the eigenvalues. So, one can show eigenvalues of A R. So, this is an exercise for you. So, these are the eigenvalues. So, now with respect to this 2 norm, so this is maximum of 1 minus 2 lambda sin square pi by 1 plus 2 lambda this is just simplified version, 2 to get cancelled. So, this is less than 1 for every lambda greater than 0. So, therefore, Crank-Nicholson scheme is unconditionally stable. Okay. So, this already we have seen, but we have seen via matrix stability analysis. Okay. So, let us check Richardson method. We have discussed these methods. So, now we are talking about stability analysis. So, this is Richardson method. A quick note, you have j plus 1, j minus 1 and j. So, this is going to be slightly different. So, the note is involve j minus 1, j plus 1 levels. Okay. So, obtaining a general iteration is slightly difficult in the sense what I am trying to say. So, this kind of iteration is a bit question mark, because since it involves 3 time levels. Okay. So, we have to do some patchwork. Okay. So, what is the patchwork? Let V I j is u I j minus 1, then u I j plus 1, then the equation above equation becomes V I j okay. Of course, then star becomes this together with together with okay. So, it is a kind of system, coupled system. Okay. So, now we have to discuss the stability, right. So, denote in the usual way E1 n, the vector corresponding to u's, then the error vector corresponding to v. So, what do we have introduced a v I j. So, let us denote the corresponding v vector as v capital V, u vector as capital U, and this is the value satisfying exactly by the difference scheme, okay, and this is the round of error. Okay. Since we have a v, so we get a corresponding error, and we have u, this is the corresponding error. So, this reduces to this will be minus 2 lambda j I So, let us see closely. So, this is so when we introduce this notation E n plus 1 here. So, here we get E n plus 1 and here E n is multiplying. See, when I equals to 1, this is in the boundary term, right. So, this is minus 2 lambda. So, this whole thing can be put it into a matrix J, okay. So, which has a specific behavior. So, if we pull out a minus and attach to minus 2 lambda, the behavior of these can be given to a matrix J. Accordingly, J will have so J has this structure. So, this call it now H. So, this is a patchwork we have done in order to obtain this kind of iteration. So, it is not the matrix A directly like the earlier cases. Okay. Then eigenvalues of H are those of so eigenvalues of H are those of this matrix where so these are eigenvalues of J. Okay. So, now the characteristic equation of this matrix, call it some P, capital P. So, the characteristic equation of P Okay. So, it is a good exercise to prove from here that the method is unstable. The method is unstable. So, I can give a hint. For example, if the roots are real, distinct, okay. So, you can check with the discriminant, okay. You can check with the discriminant of this, and then mu 1 mu 2 is minus 1. So, then one of them is positive. So, I am just giving a hint. So, you can prove that the method is unstable. Okay. So, I hope you are able to now, you are in a position to discuss stability of any finite difference scheme via either matrix stability or via Fourier series stability method. Okay. So, let us go for a few more examples. So, Dufault-Frankel. So, Dufault-Frankel is given by where so this is also similar to the earlier one. Then this can be written as where alpha is and the J matrix okay. Now, this is our H. So, this further can be written as H E n. Okay. So, we need to compute the eigenvalues of H. So, eigenvalues of H are those of two alpha, say eta 1 minus 2 alpha 1 0, where eta is 1 minus 2 sine square. So, this is cos. So, the characteristic equation of, so this is our P matrix of P eta mu equals to 0. Then we get from here exercise for you. You can show that this method is unconditionally stable. So, here I would like to mention a point, references. I have been mentioning G.D. Smith. So, numerical solutions to PDE, G.D. Smith. 2 is computational methods to PDE. So, this is Jain, Iyengar, Jain. So, the formal references, these are just a brief description. Formal references will be listed in the course content. So, these two books are very much helpful, whatever the notations I am using, and some of the problems, of course, I have changed the data here and there. So, you can see these books, so that you get a good idea of these methods. Okay. So, please practice as many methods as possible, especially computing the stability. Okay. So, with this at least parabolic case, we have come to conclusion kind of. Before we discuss any sort of parabolic methods, for example, other various other special cases, we may switch over to hyperbolic and elliptic coming few lectures. Until then, thank you.